So before we get into it, let's look back at writing tangent lines and the equations for tangent lines for a given curve. So let's say we have a function y equals x squared, and we want to write the equation of the tangent line at x equal to 1. Well, let's go through the process that we have gone through many times in the past. The first thing we've got to do is we've got to find the slope of our tangent line at that curve. Well, to do that, we need to find y prime. And in this case, y prime is going to be 2x. And when x is equal to 1, that gives us a slope equal to 2. Okay, now let's think about what is this? If instead of y equals x squared, if we say this is f of x is equal to x squared, well, really, we're evaluating f prime of 1. We're taking this value, our x value, that we're trying to find the tangent line, and we're plugging it into our first derivative function to find the slope. All right? And so in order to write an equation, we need a point, the point at which that the function is defined at x equal to 1. So to do that, we have to plug 1 back into the function. Well, f of 1 is simply equal to 1. So we have our point where y equals 1, x equals 1, and our slope is equal to 2. And so we write our tangent line y minus 1 is equal to 2 times the quantity x minus 1. Okay, a process that we've done many times before. And we're going to use that same process to give us a linear approximation. So let's say we just have an arbitrary function of f of x, and we want to write the equation of the tangent line at the point where x is equal to some arbitrary constant a. And using yx, f of a, and f prime of a, we want to write an equation for the tangent line. Well, we're going to do the same process. We know that the slope is just going to equal f prime evaluated at a. Our y value is going to equal f of a, and our x value is just going to equal a. And this is our x value and y value of our given point. So if we use our point slope form and say y minus f of a equals f prime of a times the quantity x minus a. All right, well, this gives us a linear approximation. And actually, if we rewrite this just slightly and move this f of a over to the other side of the equation, and we call our y our new function L, this is the linearization of any given function. And so we say that the linearization of a function is just simply equal to a function evaluated at a point plus the derivative of the function evaluated at that point times the quantity of x minus that x value, that point a. So what this tells us is that any given function f of x is approximately equal to L of x when we're close to a, whatever a may be. Okay, and you might ask, why do we use this? What's the point of this? Well, the reason we have something like this is it can take a more complicated function like a higher order polynomial or a function that has a lot of trig functions or complicated functions within it, and we can simplify it into a linear function and use this linear function as an approximation within a small range of x values. Let's look at an example here. Let's use the linearization of y equals cosine x at x equal to pi over 2 to approximate what is cosine of 1.75. So we're going to use the fact that the linearization L of x is going to equal f of a plus f prime of a times the quantity x minus a. Now, in order to do this, we need to know, well, what is f prime? Well, if f of x is cosine of x, then f prime is simply negative sine of x. And so, but we don't want to just know what our f prime function is. We want to evaluate it at our value of pi over 2. So we're going to evaluate our function at pi over 2 and our derivative at pi over 2 and plug this in. So our linear approximation is going to be f of a. So what is cosine of pi over 2? Cosine of pi over 2 is 0. And then we want to add f prime of pi over 2, so that's a negative sine of pi over 2, which gives us a negative 1 times the quantity x minus pi over 2. So really what this says is our linear approximation is just pi over 2 minus x. So what is this telling us? This is telling us at x values close to pi over 2, so some that are a little above pi over 2 and some that are a little below pi over 2, our function cosine of x acts like the function pi over 2 minus x. So we're going to use this to approximate, well, what is cosine of 1.75? So we can find what is 1.75 plugged into our function L, and that's pi over 2 minus 1.75, which is equal to approximately a negative 0.179. And so our linear approximation tells us that cosine of 1.75 is about negative 0.179. And actually, if you evaluate what cosine of 1.75 is, it is approximately 1.78. So this approximation is fairly accurate. It's accurate to at least 2 decimal places, not quite to the third, but it gives us a general idea of what the function's doing close to a given point. Okay, let's look at some other approximations that we can use. So if we have a binomial raised to a power, and let's say we have the binomial 1 plus x, and it's raised to some power k. Well, for small values of x, this function is actually like the linear function 1 plus kx. So this helps us to simplify higher order polynomials without having to expand the binomials raised to a power, and we can say it acts like 1 plus kx. And this only works for small values of x. And so you might ask, well, how small? What does small mean? Well, we're talking about values that are less than 1. Okay, so if we have small fractions between 0 and 1, then this approximation will work. Now, you might think that that is a very limited domain. Well, at times, depending on the function, that may be the only domain that we need or the only domain we're concerned with, and so this approximation can be useful. Okay, so let's look at a couple examples. Let's say we have the cube root of 1 minus x. Well, we can rewrite this as 1 minus x raised to the power of 1/3. And so for very small values of x, values between 0 and 1, this is approximately 1 minus 1/3 x. And so that's an easier function to work with, an easier function to even differentiate and plug numbers into. Okay, let's look at another one. So if we have the function 1 over the quantity 1 minus x, this is approximately 1 plus x, because really this is 1 minus x raised to the negative first power, and so that becomes a coefficient of x, and so it's approximately 1 plus x. Now, what I want you to do is I want you to pause the video and try C and D here, and come up with a linear approximation for these two functions. So pause the video real quick, write them down, and then when you press play, I'll have the answers up here for you. So for part C, the linear approximation, since this is really 1 plus 5x to the fourth, that quantity raised to the 1/2, that 1/2 comes down and is an extra coefficient of x. So this is 1 plus 5/2 x to the fourth. Now you might ask, well, this is not a linear approximation, which you're correct, it's not linear, but it is still an approximation of how this is going to act for small values of x. And the last one here, if we have 1 over the square root of the quantity 1 minus x squared, well, that's just like 1 minus x squared raised to the negative 1/2, and so that becomes 1 plus 1/2 x squared.